Welcome, children, to Study Hub Sri Lanka. I'm so glad you could join me today. Have you ever wondered why a straw looks like it's bent in a glass of water? Or how a simple piece of glass can help us see planets and stars far, far away? Well, today, we're going to explore all of that as we dive into geometrical optics and follow the amazing journey of light. So let's start with a really simple question that gets right to the point. Why can't we see anything when we're in a pitch black room? What is the one thing we absolutely need to be able to see? Well, the answer is pretty obvious, isn't it? It's light. Without any light, our eyes have nothing to work with. Here's the roadmap for our lesson today. First, we'll cover the basics of how we see. Then, we'll look at what happens when light bounces off mirrors. After that, we'll discover how light can actually bend, how we can trap it, and finally, how we use all this science to make amazing things like lenses. All right then, let's begin. Let's start with the most fundamental idea. How does light actually let us see the world around us? We see things in one of two ways. On the left here, you can see the sun. It's what we call a luminous object, which is a fancy way of saying it makes its own light. But most things, like this rabbit on the right, are non-luminous. They don't make their own light. So the only way we can see the rabbit is if light from a source, like the sun, hits it and then bounces or reflects into our eyes. Right, so speaking of bouncing, let's talk about mirrors. When light hits a really smooth, shiny surface, it doesn't just scatter everywhere. No, it bounces off in a very neat and predictable way. And we call this reflection. And this bouncing follows a very simple but very important rule. It's called the law of reflection. All it says is that the angle the light comes in at, the angle of incidence, is exactly equal to the angle it goes out at, the angle of reflection. It's perfectly symmetrical every single time. Simple, no? Now here's a brilliant real-world example of reflection. You've all seen this on the road. A flat mirror does something called lateral inversion. It flips the image from left to right. That's exactly why the word ambulance is written backwards on the front of the vehicle. So when the driver in front of it looks in their rearview mirror, the reflection flips it back the right way so they can read it instantly. Very clever stuff. But of course, not all mirrors are flat, are they? So what happens when we start curving them? Well, there are two main types to know. Concave mirrors, which curve inwards like a cave, and convex mirrors, which bulge outwards. You see convex mirrors every single day. They're the side mirrors on cars and buses. And why do we use them? Well, because even though they make things look a bit smaller, they give the driver a much, much wider view of the road behind them. It's all about safety. Concave mirrors, on the other hand, do the opposite when you hold them close. They magnify things. And this is super useful for, say, a dentist who needs to get a really big, clear view of a small tooth. Or maybe you've seen them used as shaving mirrors or makeup mirrors for the very same reason. Okay, so light doesn't just bounce. The journey of light gets even more fascinating when it passes from one material, or what we call a medium, into another. For instance, when light goes from the air all around us into a glass of water. I'm sure you've seen this before, haven't you? You put a straight pencil or a straw into a glass of water, and suddenly it looks like it's bent or even broken right where it hits the water. This isn't some kind of magic trick. It's just physics. So that's the big question then. What is actually happening to the light that's traveling from the pencil, through the water, through the air, and finally to our eyes that makes it look that way? And the answer is a wonderful phenomenon called refraction. You see, when light goes from one medium to another, like from water out into the air, it actually changes speed. And because it changes speed, it causes the light ray to bend. And that bending is what we call refraction. Now, just like reflection, this bending follows two simple rules. First, we need to imagine a straight line drawn at a 90-degree angle to the surface. We call this line the normal, okay? So when light enters a denser medium, like from air into glass, it slows down and bends towards that normal line. And when it leaves the glass and goes back into the less dense air, it speeds up and bends away from the normal. And have a look at this table. It's amazing. It really shows you how much the speed changes. In air, light is traveling at an incredible 300,000 kilometers every second. But look, in water, it slows down to 225,000. In glass, it's even slower, and in a diamond, it's less than half its speed in air. This change in speed is the whole reason refraction happens. Okay, now this is where things get really, really cool. What if we could take this idea of bending light and push it to its absolute limit? Well, it turns out we can actually trap light inside something. To understand this, we need to know about something called the critical angle. So remember how light bends away from the normal when it leaves a dense medium? Well, the more you increase the angle you send it in at, the more it bends away. The critical angle is that one specific perfect angle where the light bends so much that it just skims right along the surface at a 90-degree angle. So here's the magic trick. If the angle you send the light in at is even a tiny bit bigger than that critical angle, the light can't escape. It just can't refract out. Instead, it acts like it hit a perfect mirror and is completely reflected back inside the material. This amazing effect is called total internal reflection. And this isn't just a science experiment, children. This principle is the backbone of our modern world. The fiber optic cables that bring the internet to our homes work by trapping pulses of light and reflecting them down a tiny glass fiber for thousands of kilometers. Doctors even use it in endoscopes to see inside the human body without surgery. It's incredible. Right. For our last section, let's bring everything we've learned together. We know we can bend light through refraction, so how can we control that bending to create useful tools? Well, the answer is with lenses. This table shows us just how powerful a convex lens, that's one that's thicker in the middle, can be. The key thing to know is the focal point, or f. Now, everything depends on where you place an object compared to that focal point. For example, if you put an object really close, between the lens and f, you get a bigger virtual image. That's exactly how a magnifying glass works. But if you put the object far away, the lens makes a smaller, real, and upside-down image. That's the basic idea behind how a camera works. And that is why understanding lenses is so very important. They are at the heart of so many inventions that have completely changed our world. From the eyeglasses that help many of us see clearly, to the microscopes that let us see tiny cells, all the way to the giant telescopes that let us look at distant galaxies, all of them are just carefully controlling the journey of light. And that brings us to the end of our journey through geometrical optics. I really hope you found this lesson helpful, children. If you did, please don't forget to subscribe to our channel, Study Hub Sri Lanka, and click that bell icon so you get notifications for our next science video. Thank you for joining me, and we will meet again soon.